Today's lesson is on section 4.6, Model Direct Variation. I'm going to make an adjustment to the title of this section though, because the book in this regard is kind of outdated for this section. What they now talk about when we talk about the 8th grade standards, what students have to know to pass 8th grade or to be prepared for the next level, is we talk about these as proportional relationships. That's the term they've given them now. So proportional. So if you're taking notes, I actually want you to change this name of this section to proportional relationships. It's really the same thing, but since this book came out, and now that they've kind of retitled, I got two dots in my eye there, but since they've retitled this section, or retitled like at least the type of equations we see in this section, they now call these a proportional relationship. But again, they mean really the same thing. So if you're going through book problems and you see the words direct variation, they're asking for the same thing as I'm going to talk about here, a proportional relationship. As I say right away in this first line, though, don't let these equations fool you. We've been working with equations just like this up until this point. Direct variation equations, or again, as I should say now, a proportional relationship equation, just looks like this, y equals mx. And so what's the difference between that and problems we've been doing before? Well, we usually have the form y equals mx plus b. But if we're saying that in this case there is no b on the end of this equation, it's just y equals mx, what does that mean? Well, that just means that b is always 0 in these cases. This is what a proportional relationship is. They say that for every number x you plug in, y always has the same ratio, the same constant that gets multiplied to get, the x always get the same constant gets multiplied to x to get to y. That's what keeps the numbers, the ratio, the relationship in proportion, as they say. So there's a certain constant that I take that number, multiply it times whatever x is, and I always get y. I don't add or subtract anything after that. So that's why b is always 0. Well, when we think about graphing these same equations, as it says here, what will the graphs of these equations look like? If b is always 0, think about how we've been using slope-intercept form to graph these equations lately. Well, what happens when b is 0? Well, that just means we start right at the origin. And we're saying for a proportional relationship that it's always of this form, y equals mx. It's always b equals 0. So anytime I graph one of these equations, what's going to happen is all their y-intercepts are going to be at the origin. All I'll need to know to graph these is just the slope. My first point will be right at the beginning, right where the x and y axes cross. I'll put a point there, and then I'll just use the slope, and then that'll be the graph of my equation. That's all the information I'll need. For this first one, the red one, if we do like we usually do, pick out m and b, well, like we said, b is 0 because it's just y equals 4x, and it's not plus or minus anything in this case. So b is 0, and my slope is 4. So if I was going to graph this, and I could write it as a fraction to remind myself, but I would just go up 1 over 4. This blue one, same kind of thing. If I was going to figure out the slope and the y-intercept, the slope would be negative 1/3, and again, the y-intercept would be 0. I would start at the origin and just go down 1 and to the right 3. For the last one, the green one, I go up 2, or sorry, it's negative, so I go down 2 and to the right 1 from the origin, and that would be my graph there. So for example, I've got some tables here, but that's just another way we can talk about them too, but I'm just going to go to the graph for now. As I was describing, there could be the graph of those 3 equations right there. The red one, the blue one, and the green one. They might look something like this. Again, the biggest thing I want students to get away from this, though, in a proportional relationship, every graph should go through the origin. So if I was making a table of these, what I would notice is I'd always have the same pattern where if I plug in, like, let's say 0, 2, or 4, anytime I plug in 0, I'm just going to get 0 because that's always the origin, right? And that's one of the points we're talking about. So anytime I would plug in 0 for x, I'd get 0 for y, so I could even fill those in right away. But let's say go back to this red one. If I plug in 2 for x, I'm just going to multiply by 4, so I'll get 8. If I plug in 4, I'll get 16. Like there's always that direct relationship where I just multiply x by something and get y. And the origin is always part of that table as well. So again, these equations, a proportional relationship equation, We just know that b is always going to be 0. If I graph it, it's always going to go through the origin, and there's just some constant that relates x to y every time. Some problems might ask you to make the equation. If they give you a table, what's the equation that models this proportional relationship? Well, I would just look for some kind of pattern, and again, the pattern should be that every time I take x and multiply by some number, I get y every time. If I look at this first table here, the red one, well, 1 times something has got to give me 4, 2 times something's got to give me 8, 3 times something's got to give me 12. It's got to be the same number every time. In this case, I think if I look at the first one, it's got to be 4, right? And that works correct. And for all the other ones, that also works too. Anytime I take x, I just multiply by 4, I get whatever y is. So that's my equation. Y equals 4x, or 4 times x. That next one, if I take 5, I get 50. If I put in 6 in this equation, I get 60. 7 in this equation, I get 70. So what must the equation be? Well, it's like I'm multiplying by 10 every time. So that's going to be my equation then. Y equals 10x. And then for that last one, I don't know if I have an orange, but I'll just kind of go back to black, I guess, for now. For that last one, if I plug in 2, 3, and 4, I get negative 6, negative 9, negative 12. Well, looking at that table, what's the pattern here? What am I multiplying x by every time to get to y? And is it always the same thing? Well, it's giving me a negative number, so every time I multiply something, so it should be negative something. And 2 times 6 is 3, or 2 times 3 gives me 6. 3 times 3 gives me 9. 4 times 3 gives me 12, so it must be 3. So times negative 3. So y equals negative 3x. So again, these kind of tables, if they ask you to write the proportional relationship or what the equation is for it, then I just gotta look at what is that number that always gets multiplied to x to give me y every single time. Some problems too might ask you, is it a proportional relationship? And just by looking at the table, you have to figure out, well, does this model a proportional relationship or not? Again, a question in the book. I've still got the book kind of how it describes it up here. Because I do want you to realize that if you see a problem in the book and it says direct variation, well, again, what I'm telling you, though, is the new way they're going to talk about it is proportional relationship. But if you're doing a problem from the book, you do need to know what this means instead. So just kind of know that if they say direct variation, it's still what we're talking about today. So it might say something, does this table model a direct variation? Well, what I would want you to think is, does this equation model a proportional relationship? Now, as I look at the first table here, again, I would try to find that pattern. Is there always something that they multiply by x to get to y? And then that's the only thing I can see. The only connection is there's not added or subtracted anything else. There's no other way to get the variable or get the value for y. Is it just always multiply x by something and get y? And if it's that same number, then yes, we got a proportional relationship. Well, 4, plug in 4, I get negative 8. Plug in 5, I get negative 10. Plug in 6, I get negative 12. Looks like everything's doubling and just becoming negative, so I'd say y equals negative 2x. Yes, I think this one is a proportional relationship, this table. And all I'm doing is multiplying everything by negative 2. This next one, am I multiplying something 2 by 2 to get 18? 3 to get 27, 4 to get 36, and is it always the same thing? I think so. If I multiply everything by 9, I multiply all the x values by 9, I get whatever y is, the y value is. So I'd say yes for this one too. And the equation would be y equals 9x. I take whatever x is, and I multiply by 9, and that's all I have to do. This last one, well, if I multiply 1 times 6, I get 6. But 2 times 4 gives me 8. 3 times something with a decimal or some kind of rational number gives me 10. So this one's not multiplying by the same thing every time. So I would say no, this is not a proportional relationship. What I want students to still realize, though, is there's nothing wrong with this table, nothing wrong with this equation. But in this section, they're looking for us to identify these types of proportional equations. There's these relationships right here and what they look like in their equation form and in their table form. So in this case, we're going to say no, that third one is not a proportional relationship. You probably could make the equation for it. There's ways to do that, but we just don't have to for this section because we're just focusing on these first two. One other type of problem they might have you do in the assignment today is they might give you just an equation and tell you and ask you, is it a proportional relationship or not? And so again, what does that look like? Well, it looks like y equals mx. So if it's just some type of equation where I have it solved for y, and then I have a slope and my term for x, but nothing else, then I'm going to say yes, that's a proportional relationship. Again, I've got the directions up here that say direct variation, just because that might be what you see in the book, though. But know that we're really talking about, and now that that this book is just a little old, this is one section that is a little outdated. Most of the other sections are pretty good, but this one, the new term they talk about is a proportional relationship. So that's really what we're trying to find. Even if they say direct variation, that's just kind of the old way to say it. So this first one, y equals negative 6x. Well, does this one look like y equals mx? Oh, yes, it is. Okay, or yes, it does. It just has some number times x, and that's all it's got. B would be 0 for that equation, so I'd say yes, that's a proportional relationship. This second one, I would say no. It's y equals 2x, but then also plus 1. So this would make it no. It's a good equation. There's nothing wrong with it. It's just not a proportional relationship. This third one, just like I talked about above, though, I need to know if the equation is y equals mx, if it looks like that. So I still need, like we've done in the past and like we've practiced, I still need to get y by itself, or solve this equation for y to tell for sure. So what I have to do in this one is divide both sides by 2, just like we've done many times. I get y equals 3x, and I could say yes, this is a proportional relationship. We'll just look at these last 3 examples I have on the board here together. Same kind of thing as we were doing before, though. Are these equations a proportional relationship or not? Again, the first thing I have to do, though, is I got to get solved for y. So if it's negative 5y, first thing I'm going to do, oops, my page jumped on me there. But the first thing I'm going to do is divide both sides by negative 5. I just got to divide every single term by negative 5. When I do that to this side, the negative 5's cancel out. I just get y by itself. That's what I want. On the right side, I get negative 3x. And then 5 divided by negative 5 gives me negative 1 or minus 1. Is this a proportional relationship? No. Is it a good equation? Could we graph it? Could we make a table? Yeah, we could do all those things. It's just not the ones they're looking for right now. It's not a proportional relationship. Number 5, I don't even have to do anything with this one. This one is solved for y, so just kind of realize that. It's just adding 6, but that's not a proportional relationship. When we have one of these types, it's just when we have something multiplied by x, and that gets us to y. That's the relationship between the 2 variables. So in this case, they're just adding 6 every time, but that's not what we're looking for a proportional relationship. And this last one. Again, what I got to do is get y by itself first. I have 4y plus 3x equals 0, and this one's just a little different because we're not used to seeing maybe 0 on the right side there. But still, one we can do. What do I got to do to start getting things away from the 4x? Well, what I'd do is I'd subtract 3x from both sides first. That would get rid of it from the left side, so now I just have 4y on that side. On the other side, 0 minus 3x, well, 0 minus anything would just be whatever you have. So in this case, yeah, the 0, I don't need to write that in again. It's just going to be negative 3x on that side. And then to get y by itself, or solve the equation entirely for y, I got to divide both sides by 4, and I get negative 3/4 x. And this, yes, is a proportional relationship. It is a fraction, but that's okay. It is still just some number multiplied by x, and that gives us y. So I would say, yes, that's a proportional relationship. So again, what are the big things I just want students to make sure they understand what a proportional relationship it always looks like? Y equals mx, so there's always that constant ratio between x and y. And if I make some kind of graph, the other thing I want them to understand is if they make some kind of graph, that any graph they would make would go through the origin. So the point 0, 0 in a proportional relationship, the point 0, 0 will always be the y-intercept.